Thank you for being here today. I'm going to talk about a new analysis type which allows to recover what your app is waiting for, but with kernel tracing, not user space tracing. I'll show you why. Let's start with an example. Let's say you are a developer of apt-get, a very useful program. You would run a traditional profiler on that execution. The profiler will output you the instructions executed by the application itself. But since apt-get is a kludge of many processes that either waits for something else to happen, it becomes very complicated to understand the overall execution latency. So what we are focusing today is on the blocking part of any application. If you're computing a Fibonacci number, then if it's a standalone app that doesn't talk to anything, it's less interesting. We really are targeting distributed application of any kinds. Let's say you are web developers. Then you're trying to profile your web application and your loading time. You would want to know what the server is doing while the client waits. So this is the question we are trying to understand, but with kernel tracing. Here is an artwork of a trace. I love kernel tracing. If we are going to get into it, we would see patterns of processes that are creating other processes, wait, contention on the CPU, and interrupt handlers, page faults, everything, except, of course, the code of the application itself. So sometimes we need to guess a little bit of what's going on in the application side. I like this because it is universal. The user space application cannot escape it. We can trace viruses, for instance. It is distributed, as we show, as Geneviève showed. We can trace multiple machines and synchronize the traces to get them together. And the goal to get the complete view across machines allows to pinpoint easily the performance problems that can be the network, the server, or in my experience, it was often the DNS server that was finally misconfigured. Anyway, here is a graphical view of a kernel trace. The green is the state representing running. The blue is the system calls. When an application wants the CPU, so it is the state task running for the kernel point of view, and it cannot because the schedule decided that this thread has exhausted its time slice, for instance. It gets the preempted state. And of course, if there is a blocking always occurs on kernel mode. Then we get the blocked state, which corresponds to task interruptible or task uninterruptible for Linux. So I say blocking always occurs in kernel mode. It means also that blocking is not visible in kernel mode, the same thing as preempted. So what is the culprit or the core idea here? We can know what the application was waiting on from the origin of the wake-up signal. So when a task is blocked, it is put in a wait queue. And the wake-up signal on Linux will take the task in the wait queue and put it back on the running queue. So the source of the wake-up is critical to know what the app was waiting for. In that first case, a device was doing the wake-up. So let's say the soft ERQ, you can check that in proc soft ERQ, you have all the list of soft ERQs. If the wake-up comes from an interrupt handler, which is the timer, then we know that the application was waiting for the timer expiration. And all other type of soft ARQs or hard ARQs can trigger wake-ups. Task wake-ups, the wake-up is emitted from a system call. In that case, that could be a consumer and a producer. So the consumer would block until the producer produce some data. But it can be the reverse direction. The write could block, waiting for the client or the consumer to consume and empty a little bit of the data. For instance, in the case of pipes under Linux. So the idea is to replace, in that case, the blocked state with for that interval and display what the task was waiting for, in that case, the task itself, the subtask. In the case of a remote wake-up, we follow network events across machines, and we backward follow the links to identify the thread that produce finally the interesting packet the application was waiting for. So the required events are the scheduling events, of course, the sched switch and the sched wake up. We also, and for newer kernels, we need a special module in the LTTNG module add-ons, because the wake up is now made in IPI. It's a little bit tricky, but it's just that we lose the dependency between the waker and the wakey. So for newer kernels, we need to add a key probe, which is slower. But this is something I would like to fix at the conference, discuss with more technical people on that side. So this is very important. But we need the ERQ handlers, entries and exit, to get its status. Let's say if an event occurs, we want to know if it occurs from interrupt or not. And we need packets. We actually added net filter hooks to get the TCP headers, part of the TCP headers, just to match the packets. And at that point in the kernel stack, the packets are defragmented also, so there is a one-to-one match. But no, the important point here is that no system calls are required. It means it doesn't assume that a send and a receive are involved into a query. All right? We can produce that analysis without system calls. Of course, we are tracing them because it helps the developers to understand the overall execution. So with the trace, we are building a graph. The horizontal edges represent state changes. Vertices are events. And the vertical edges are links between processes, either wake-ups or network exchanges. There are various ways to then traverse the graph and get properties. And in this case, we replace recursively every blocking on the path with the source of the blocking. So we get a trace where every blocking is identified with its cause. The analysis overview with LTTNG, it starts, you can do it either offline or getting the trace online with RelayD. It works both. I prefer right now to use offline mode, so copy the trace afterwards, because the tracer is traced and its packet also. The trace is much bigger when we're using the live streaming mode. So to reduce the trace size, I'm using the offline mode for now. So we start tracing on these machines, all the machines we want to trace. We get the trace, synchronize it, build a graph, and then compute the critical path or the active path of the application. So without any further discussion, I will show you what it looks like. I'm going to close the traces function here. I have a few examples to show you today. The first one is a local application, it's a script shell that does DD, pipe grep, pipe exdump. And not a good idea. So here we have, I will select the view, which is the critical flow view here. And by selecting the script I was going to show you, it will compute the dependency between the processes. So we start with the DD process that outputs some data in the shell script, and we see the interaction with each processes. And what is interesting is that if we change actually the size of the DD buffer, you know, the BS and count, it's going to change the way the pipeline is handled. It's very interesting to see that. We have a sort also. The sort returns only when it has all the data. So we see like that the execution, the parallelism is limited by the fact that we have a sort in the pipeline, and the other stage cannot proceed until all the data is processed. So this is a local process, only one trace, but it shows that it works with the base case. One thing I was wondering, and I never understood, is how mount work. Here is a CIFS mount. I trace the client doing the mount and the server. Look at that mess. Okay, it starts with the mount process doing a request to the server. And it takes about 20 milliseconds for the server to reply. But then mod probe is also involved to load the correct modules. We see also this section is very interesting because it involves a lot of kernel threads, threads related to journalization of the server itself, the file system, and a large sink of, you see here, the block device of the journalization GBD2 thread of the first drive. It has nothing to do with mounting a shared drive, but all the disks are synced. So it takes 20 milliseconds. So we can drill down on that and see all the links between the processes involved in the request. There's another thing I would like to show you. It's the listing directory of a CFS drive, network share. If I'm zooming in the ls process here, all right, I'm zooming in a lot. We see the exec and all the system calls. And one of them is get ends. Get ends. It's usually not sending packets, right? But it does in that case because the VFS layer underlying this system call is implemented with CIFS. So ls is a distributed process in that case. It sends packets on the network. Beware if you're trying to do a security system. This is the advantage of not assuming anything about the system calls. Any system calls can send packets. If you're doing an IOCTL, you can do whatever you want. You can contact the NSAD, for instance. That was a joke. Here is the critical path view. So we can see the time spent by the server replying to that request. And the special thread that is key thread D, that is listening for and providing that information to the final client, which is ls. And we see all the page faults of the server that are involved into the processing of that specific listing directory. And there's also quite a few things, because this command is actually executed through SSH. We see the SSH daemon involved when the standard output is triggered, and that SSH actually also contacts dbus daemon. We may ask Leonard why, but that seems to be special. And the last example I do have today is an example with a web application. It involves three machines that are traced at the same time, and then we are doing three things. It's a form, it's Django app. You can implement it for yourself if you want. It's the tutorial, the poll web application, and we see, well, it's a little bit strange, but believe me, this is the client process. This is the view that does not show that. We use Mechanize to make automated requests to the server. So we see that we have 18 millisecond blocking, and 32 here, and a large one here, 117 milliseconds. If I'm going back to the slide, if you remember, we were waiting to about 20 milliseconds for that request to be done in the Chrome panel. So this is what's going on under the hood. It contacts Apache. Then the Apache thread dispatches itself to a worker thread inside Apache, and then Apache itself contacts PostgreSQL. This is totally unmodified setup. It works without any instrumentation of the user space in the user space. The downside is also that I don't know what are the SQL queries that I'm working on. So, of course, having another layer of user space trace would be awesome. But at the same time, this works for every application. So how does all the requests took as the time? We can measure it by scrolling. It's about 19 milliseconds. So the blocking window, almost all the blocking window. Here's the interesting part. There are three parts in that trace. The first one is the form. We get the form. Here we post the form. And there's a third redirect. So when we post the form, we are actually saving data to the database. So we see that sync that lasts 7 milliseconds. We can drill down to the device that involve delays in the request. All right, so I just lost my PDF. All right. So in conclusion, we were able to cross machine boundaries using only kernel tracing. The trace synchronization we are using is appropriate for a small number of machines. It allows to do reverse engineering, in fact, of execution, which is very nice, and discover sometimes things we would not expect, because we're using a lib, and that library does fancy things. It has precise and universal tool that is independent of user space runtime, which allow to monitor any application. I would be thrilled to see performance counters of the active path. I think this is the next step for the developer point of view. Such as, for instance, knowing where the system calls are made in the application. So we need a stack trace for that. On more performance side, we would need filters, good filters to avoid tracing the tracer itself that adds a positive feedback loop into the overhead. And also, the current analysis works for, let's say, mid-sized traces below 100 megabytes because the whole graph is kept into memory. That would be necessary to add on-disk representation of that graph to make it more scalable. So this is another area for future work. I would like to thank my professor Michel Dagenet and our partners Efficios and Ericsson. Special thanks to Geneviève to review my messy code. And if you are interested to know more about this analysis, you can go to my webpage and additional information. You can download the trace, you can download the code, you can download even the standalone Eclipse application and have fun with it. Thank you. Any questions?
Could you go back to the previous slide, please? Could you explain what the performance counters, what you mean by that? Are those derived from the trace data, or are they something else?
Yeah. Sampling application allows to detect the hotspot in the code. So we would be able to know, let's say we have some intervals here. I could swipe and select an interval and see what the code in the application would be doing. Performance counters allow to have an interrupt when a certain counter value reaches 0. And for instance, you can count instructions, page faults, but not page faults, yeah. It's not an hardware performance counter. I mean, memory cache misses. And these data would be very interesting to see that in the viewer itself, and you would be able to spot, let's say, the region of the execution that has poor IPC or poor memory cache, and focus your effort on these areas as a developer. Perf is doing it, but we cannot filter it. It's like an average of all the execution, so you'd better select a very narrow function to trace.
I'm not sure. I think we integrated. We use the Python interface for reading perf data, and we get stack traces for these samples. I know what you're using for reading the trace data, but maybe that's an option.
Yeah, that would be awesome. In fact, I think we need to get specific code for each language and framework to get the stack traces. From the kernel point of view, it's just instructions, and to get the real meaning of what's going on, we need another layer. But at the same time, since blocking and preemption is not visible from the user space side, and that it allows to instrument and have that foundation on which you can understand higher level behavior. Yes?
Hi, so if I understand it, you can go from any blocking request and then using the dependency graph, trace it back to the origin, the real context.
Exactly.
So, I mean, this is really exciting stuff because I consider issues of CPU usage just solve the problem because we can profile what's on CPU very easily. But when we're blocked on something and there's one layer of interaction or two layers of interaction, things get really complicated. So I'm excited to use this. So just to get my head around it, really because you're tracing all of them through the wake-ups, it doesn't matter if there's 5 levels deep, I can understand I was blocked ultimately for this other.
Exactly, there is no limit on the depth of the recovery.
So when I tried this, although I was using dtrace, I found overheads to be an issue because I had to trace all scheduler wake-ups and all scheduler on-CPU, off-CPU events. This isn't something that you've had a big issue with the overheads. Okay,
the overhead, most of the events are sched switches. I did an experiment where we tried to trigger sched switches at the highest rate possible with a semaphore. I got 150 sched switches per second on my machine. At 200 nanoseconds per event, and the latency for the sched switch, it involves at the maximum rate 12% of overhead. Usually, this is the maximum outbound, the worst case execution time. And the usual overhead for sched switches, which are 90% of all the events in the normal case, it is about 1 or 3%. For I/O jobs, the overhead is because of the split bandwidth with the tracer. So maybe if you have a very intensive I/O load, taking a different disk for the load and the trace itself is solving the issue. And as for the network event, this is an issue because it's very, very high frequency. So you'd better have filters, and this is something we should look at to get the packets, only the packets we need for a specific analysis or, let's say, filter for certain application or connections. Yes, definitely.
What is the name of the tool that you as here?
It's Trace Compass.
Excuse me?
Trace Compass, the tool that was presented through. Yes, it's an Eclipse plugin, and you can download it. It's on the webpage of Geneviève.
Mm-hmm.
It's also standalone.
It's in the standalone. It's just that it's beta software. There's a certain time when the research thing goes to production. And the current state is something that is a prototype.
Mm-hmm. And also, can I produce the traces on one machine and then load them into the...
On one machine, yeah, the first example I showed is an example on the local host. And if you're interested to trace on multiple hosts, I wrote a small application, it's called LTTNG cluster. It's going to spawn traces in parallel on multiple machines, do the tracing job, gather the traces, and it automates the process. I think I'm running out of time, right?
Yeah, maybe one last question? No? Okay, thank you, Francis.
Thank you very much.